Now let's see what happens if we have two wires, each carrying some current I, and they're located a little bit near each other. It turns out that the two wires will either attract or repel, and whether or not they attract or repel is related to the relative direction of the current in wire 1 compared to wire 2. Let's take a closer look at this. So suppose we just have one wire. That wire carries some current I, so we can draw it here. Let's say it has some current I, and we'll call this wire 1. We know from previous study that a wire carrying some current I creates a magnetic field in the space around it. And that magnetic field produced by that wire, so magnetic field produced by wire 1, its magnitude is given by mu naught I, let's call this I1, divided by 2 pi r. And I'm going to actually write d here, and we'll see why in a minute, but d is just the distance away from the wire. And remember, we will derive this equation later on. For now, we'll just take it as a known fact that that's the magnitude of the magnetic field created by one wire. We can find the direction of that magnetic field B1 using our right-hand rule for wires. And if we were to do that, we would find that the magnetic field on the left side of the wire is directed out of the page, and on the right side of the wire, the magnetic field is directed into the page. So out of the page on the left, into the page on the right. Now suppose we have a second wire, wire 2, and we place this wire, so there's wire 2, some distance, d, away from wire 1. What happens? Well, let's assume wire 2 also carries some current, I2, and we know that if we have a wire that carries a current and it's placed in a magnetic field, a force will occur. And actually, that's what's going to happen to wire 2, because wire 2 is placed in the magnetic field created by wire 1. So we can find an expression for the force that wire 2 would experience when placed in the magnetic field created by wire 1. To do that, we'll need our new equation that we just derived and we talked about at the top of the page, which is force is equal to I-L cross B. In the context of wire 2, we'll write this equation as follows. The force between the wires is equal to, because we're looking at wire 2, current 2 times the length, and let's just assume both wires have a length L. And then we'd have cross, what's the magnetic field? Well, it's the magnetic field produced by wire 1. If we were then to find the magnitude of this force, here's what we'd find. Force between the wires is equal to I2 L B1, and it would be sine 90 degrees because our current and our magnetic field are perpendicular. We have an expression already for B1. So substituting that in, here's what we'd find. The magnitude of the force experienced by wire 2 from the magnetic field created by wire 1 is given by force wires equals mu naught L I1 I2 divided by 2 pi times the distance between the two wires. And if we were to repeat this process where we found the magnetic field created by wire 2 and then found the force on wire 1 by that magnetic field, we'd get the same expression that I'm now boxing. This idea that wire 1 creates a field that then exerts a force on a second object should be familiar to us because it's very similar to what we saw for the electric force between charges. So in words, let's just write one more note going over this reasoning that we've just talked about. So this is similar to what we saw with the force between electric charges, in that, in the first step, wire 1 creates a magnetic field. We called that field B1. Then, a second object, in this case wire 2, is then placed in that magnetic field and experiences a force. So wire 2 with some current is placed in the field B1 and experiences a force. Now we said before, two wires, each carrying some current I, will either attract or repel each other. Let's now see if we can figure out, using our right-hand rules, what's the situation where the wires would be attracted to each other, and in which situation would the wires repel each other. So let's move this to there so we can still see our equation, and now let's practice our right-hand rules. These diagrams show one case, the one on the left, where our two currents are in the same direction, and in the case on the right, where our two currents are in opposite directions. And there's also some dots and X's already drawn in for us, indicating the direction of the magnetic field. But I find that these figures are a little bit confusing, so let's actually try to just derive for ourselves how the author of the figure got the dots meaning field out of the page and the X's meaning field into the page. So if you have a different color, that will be useful here. So I'll switch my color to, let's choose green, and let's color in the top wire here. Let's make it a bigger marker. This one green, and green over here as well. So what you should do now is pause the video, and for the wire that has current I1, the top one, use your right-hand rule for wires to determine what is the magnetic field produced by this wire, and go ahead and draw that in. At this point, we're pretending wire 2 isn't even there, so let me switch back to green, and using my right-hand rule for wires, I would find that for wire 1, the field created would be out of the page in the region of space above the wire and into the page in the region of space below the wire. And that's what these X's right here that I'm now going over in the figure are indicating. That wire 1 creates a field into the page in this region of space. So fill in there. And the same thing is true on the other side of the paper, because our current is in the same direction. So out of the page, above the wire, and again into the page in the region below wire 1. So finish up putting the X's here. Now let's see what happens to wire 2 placed in that magnetic field created by wire 1. So let's go ahead and color wire 2 blue. So blue there, and blue there. So now what I'd like you to do is again pause the video, and ignoring wire 1, so actually let's see, I could do this. So ignoring everything here and focusing just on wire 2 down below, see if you can derive for yourself, using your right-hand rule for cross products, that the force on wire 2 is directed up the page on the example on the left and down the page on the example to the right. So using our right-hand rule for cross products, we indeed find that the force on wire 2 in the example at left is directed up the page, and using right-hand rule again for the second example, the force on this wire is directed down the page. Now let's repeat that same reasoning, but this time using the magnetic field produced by wire 2 to find the force on wire 1. So let's bring back wire 1. It looks like I lost my green, so I'll recolor this one real quick. All right. So there we go. Now let's find the direction of the magnetic field produced by wire 2, the blue wires. So pause the video, use your right-hand rule for wires, and determine the direction of the magnetic field from wire 2. Using right-hand rule for wires, we find that in the region of space above wire 2 on the example to our left, the magnetic field is directed out of the page. So I'll go ahead and color in these dots that were already there for us, and we're indicating the magnetic field produced by wire 2 in the first place. On the example on the right-hand rule tells us that because the current is now going to the left, the magnetic field above wire 2 is directed into the page, and that's what these X's were signifying originally as well. So go ahead and draw these as blue, showing that they are produced by the bottom wire. So now let's see if we can find the force on the top wire because of the presence of the magnetic field produced by the bottom wire. And I know that they're already there, but let's pretend that they aren't. So again, ignoring everything down here and focusing just on the top wire and that magnetic field, let's pause the video, use right-hand rule for cross products, and find the force on that wire. And so, using our right-hand rule for cross products, we indeed find that the force on the top wire on the left is directed down the page, and for the wire at top on the right example, force is directed up the page. So now let's bring back wire 2, and again I lost the color on that wire there, so do it again. There it is. And we see that indeed in the example where current is in the same direction at left, each wire experiences a force such that the two wires are attracted to each other, and at the example on the right, where the currents are in opposite directions, each wire experiences a force where the wires are repelled from each other. And this is actually opposite of what we're used to. So let's write this down before we forget. So fill in the blanks. Parallel wires carrying current in the same direction attract each other, and parallel wires carrying current in the opposite direction repel each other. And so let's make a note, because this is the opposite of what we're used to, where in this case, same current direction leads to attraction, whereas for charges or magnetic poles, same always led to repel. But for current carrying wires, that's not the case. Same current direction leads to wires attracting, whereas opposite directions of current repel. And this is different than what we're used to.